Hi, class. I hope you're all doing well. We are rapidly approaching the end of our time together. So we have lecture today and lecture on Friday, and then we will be done for the quarter. So we're trying to wrap everything up and tie together all the various things that we've been talking about. So today and Friday's lecture will kind of try and synthesize a whole bunch of different things that we've been learning and thinking about as we go along. I know many of you are in major areas which are experiencing unrest right now, so I do hope you are taking care of yourselves and staying safe. If you're participating in any of the protests, please do be aware of yourselves and your surroundings and take care of yourselves, okay? Okay, so what we're going to do today is we're going to return to the Drake equation. So the Drake equation we introduced early on as a way to think about life in general, but its original purpose was to think about intelligent life in the universe. And so now that we've had some long discussions about all the different aspects of life and about intelligent life, let's return to it and talk about what its original purpose was and what we think it's actually telling us about the cosmos. So in the background here is the famous plaque of the Drake equation, which you can see. So Frank Drake famously proposed this at a conference at the National Radio Astronomy Observatory in Green Bank. And if you go to the Drake Lounge there at Green Bank, you can see this plaque on the wall. So this is the Drake equation right here. You can see n, the number that we talk about. You can see all the classic numbers that go into the Drake equation. So you'll recall that your book does not use exactly this notation. It uses slightly different notations, but this is the notation that I've been using all through the class because it's the notation that I learned it in, and it's the one that still kind of makes the most sense in my brain. But it's translatable into all of the other notations that you're familiar with. Okay, so let's talk about it. I'll go ahead and start a few slides. Okay, so as we said, the Drake equation was originally meant to be used to think about the number of extraterrestrial civilizations that exist in the galaxy at any given moment that would be communicable with us. Okay, and so when we've used it in the past, in particular, if you go back to the second or third lecture of the quarter, we had eliminated all of the quantities that had anything to do with intelligence or technological communication. So in this figure here, the two pink numbers there in the center, we eliminated, and we use the rest of the equation to think about life in general. So what we're going to do this class period is we're going to go back and revisit some of these numbers, talk about the values that we think they should have based on things that we've learned this quarter, and then we're going to fill in those terms that we ignored the first time we visited that. Okay, so this half of the lecture, we're going to talk about astrophysics and planets. We'll talk about the nature of life, intelligence, and communication. And we're going to frame all of this, set it up so that we can look at the Drake equation in the context of these two principles that we've talked about, the rare earth hypothesis and the principle of mediocrity. Okay? So this is the Drake equation in its full extent as we have seen it before. These first three terms are the first three that we're going to talk about. These are the ones that, remember, we said are astrophysics related. Okay, so they have to do with planets and stars. The second three, in fact, the last four, are all about the nature of life itself. And so for this half of the lecture, we're just going to focus on these three that have something to do with life. The second half of today's lecture in the next video will focus on L, because L's a little bit more complicated, and it's actually different than all of these six numbers for reasons that we'll explore during that half of the lecture. Okay, so let's focus on these astrophysics numbers to start with. So you'll remember when we first were talking about the Drake equation, we kind of made some guesses, or we used some basic knowledge that we had about what the values of these numbers should be. So these were the values that we took at that time. R star is the number of stars born per year in the Milky Way galaxy. FP, at that time we hadn't studied exoplanets. FP was the fraction of all stars that we think might have planets around them. And NE, we hadn't studied habitability at that point. NE was our guess at how many planets in a solar system might be habitable by life. And you multiply those three numbers together for the astrophysical quantities that are needed in the Drake equation, and it gave you a total of 6. Okay, so let's focus right now on this one, on the fraction of stars that have planets. So we studied exoplanets for about a week in the middle of the quarter, and one of the things we had talked about was, at the time the Drake equation was proposed, and certainly all the way until I was in graduate school, we didn't know of any stars with planets around them. So we were really guessing about what the probability was that planets appeared around stars. But what we've discovered since we've started discovering planets so readily, and we have such good techniques now for looking at exoplanets, is that it seems like every star system very likely has one or more planets in it. Okay, so right now, if you ask most planetary astronomers, they will tell you that the fraction of stars with planets around them is probably very close to 1. There are certainly going to be stars that don't have planets, but when you're talking about 400 billion stars, and I just randomly pick one out of the sky, what's the probability that they're going to have a planet around them? It's going to be extremely high. And so that means take FP to be about 1. Okay, so if I just go back to my calculation over here on the left side, and I replace FP equal a half with FP is equal to 1, then that makes that whole astrophysics quantity jump up from 6 up to 12. Not a big jump, but it's a jump that makes differences. Okay. Now, the other part of that is NE, which is the number of planets that could be habitable. And when you talk to people about this, they will sometimes have the view that what you're really asking about is the habitable zone. Okay, and if you haven't thought carefully about habitability, that's the most natural thing to think about, is we're talking about planets and we're talking about the habitable zone. And so when we talk about the Earth, or the solar system, then NE is roughly 2. It's Mars, which is on the outer edge of the habitable zone, and Earth, which is in the middle. Some people might say 3 because Venus is just beyond the inner edge, but it's on order 2 or 3. But this idea of the habitable zone ignores the fact that there are many other places in the solar system that might be habitable life that aren't in the habitable zone. And in particular, when we look at moons in the outer solar system, in particular Europa, Titan, Enceladus, when we looked at Ceres in the asteroid belt, right? There's all kinds of other places in the solar system which have other sources of energy rather than just energy from the star that might make them habitable. Okay, so the number of habitable worlds doesn't necessarily need to be the number of worlds in the habitable zone. Okay. Furthermore, if you were just thinking about the architecture of solar systems, like the architecture of our own solar system, then you might think the number of habitable zones, habitable worlds in the zone is small, like 1, 2, or 3. But when we see exoplanet systems now, we see architectures which have many worlds squeezed into the habitable zone. And so down here on the bottom is this picture of the TRAPPIST system that we had talked about several weeks ago, where there are 5 worlds in the habitable zone of the TRAPPIST-1 star. Okay, so these low numbers for the number of planets that might be habitable seem small based on our current knowledge that you and I have after studying exoplanets for a little while. Okay, so if I were to go back to our calculation there, and so now look at the number of worlds that might be habitable, before we had taken that to be 2, Earth and Mars, say, okay, and I can now replace it with a larger number. And the question is, what larger number should you use? Well, given the TRAPPIST system has 5 worlds, if I were to look at the solar system and just take the Earth and Mars and the 3 most obvious Jovian moons, I might say 5. And so if I take 6 times 1 times 5, then the astrophysics gives me 30. Now, you might object to that because there may be other worlds. We can certainly start counting worlds and get more than 5 if we include Ceres, if we include Ganymede and Callisto, which may not be as habitable as Europa, but maybe they still have liquid oceans down deep. Pluto clearly has something going on inside it. There's resurfacing, so it possibly has a liquid core too, right? So that number could be much larger than just 5 even. So if you wanted to be super optimistic, and we'll let you be super optimistic, you could make the number of habitable worlds be 10. If you made the number of habitable worlds be 10, then the astrophysics number would be 60 instead of 30. Okay? The Drake equation, using the Drake equation, is all about picking and choosing what values of the numbers you think are reasonable. And sometimes we'll say, well, what if the numbers are like this? And we'll get a very large number. Sometimes we'll be pessimistic and we'll say, what if the numbers are like this? And we'll get a very small number. But that's the power of the Drake equation. Not all of these numbers have been measured. And so part of trying to understand what we should be measuring better, what we should be trying to understand better, is exploring what the implications of the equation might be based on what these numbers might be. Okay? Now, FL is, of all the habitable worlds in the solar system, what fraction of those develop life? Okay? Now, what I will point out immediately, that's the first bullet point right there, is until we find other life on other worlds, we can only guess at what the value of this number should be. Now, there are certainly colleagues of ours who think this value should be very close to 1. And their argument for that is that life on Earth arose very rapidly. Very soon after the formation of the Earth, we see evidence for cyanobacteria, the very first prokaryotes, in the fossil record. So that kind of implies, together with the plentitude of organic components and liquid water and all of that other stuff that we see around the cosmos, that implies that maybe the appearance of life in any form is easy, in which case FL would be a very high number, okay? Other people are more pessimistic because we really don't understand how life started, and so FL could be a very tiny number. So these two values here, I'm not going to monkey around with this one too much, but these two values here are the values that you and I talked about during the early part of the quarter. So that 1 in a million chance is a very pessimistic estimate of what the opportunities for life on the world might be. Okay, so that will lead to the rare earth hypothesis without fail. Earlier, we had said that the principle of mediocrity suggested that life appears more readily, and we had chosen 1 out of 100 worlds. So 1 out of every 100 worlds in the habitable zone, the chemistry is just right that it forms life, at least simple life, the way it did on Earth, very easily or very readily. Okay? But what I'd like to suggest to you, what I'd like you to think about, is that even that estimate, in invoking the principle of mediocrity, may be too pessimistic. And the way I could convince you that that estimate may be too pessimistic is to look at our own solar system. So if I look in our own solar system, you and I had guessed there are maybe 10 potentially habitable worlds. Earth, Mars, Venus, Ceres, Europa, Ganymede, Callisto, Enceladus, Titan. Okay? There is about 10 worlds that might be habitable here on the solar system, and out of those, 1 has life. So observationally, based on potentially habitable worlds and the number of worlds on which life appears, we really should take FL to be 1/10. Okay? So if we really wanted to rely on observations, it suggests, based on those observations, that the number should be higher than 1/100. Okay? So in that case, let me call that the optimist case. Okay? So the optimist case, how come I didn't advance? Okay. The optimist case there is 1/10 instead of 1/100. Okay, so you begin to kind of see why using the Drake equation is a little bit difficult, but you have the skills and knowledge and ability right now to kind of think about the things you know and the things you've heard about and the way that you, as an astrobiologist studying the universe, will want to think about the Drake equation and use it to guide your future observations and future investigations. Okay? Now, I will note one other thing that we talked about, which is panspermia. And so panspermia could make this number much higher because it could take all the worlds in the solar system and spread life between them. Now, panspermia is an idea that we have talked about because we know that we find rocks, asteroids from one world in the solar system located on another world. We talked about the Allen Hills 84001 meteorite, which came from Mars, but we found in Antarctica. Okay, but we have yet to find evidence that life has made the hitchhiked journey from one planet to another. So we don't know that panspermia actually could transfer life from one world to another, but it's certainly not a possibility that we can exempt ourselves from at this point. Okay? Okay. Now, what about the other life numbers? Well, there's intelligence, okay? And I'll make that same caveat. Until we find other life in the universe, we can only guess at what the value for the fraction of worlds with life, of those, what fraction have intelligent life, okay? So I have here in the illustration a chipmunk, okay? And a chipmunk is a great example of this, right? So on Earth, intelligence is widespread, right? We've talked about humans, we talked about how crows use tools, dolphins, whales, they have clearly complex language, cats and dogs, chipmunks, wolf spiders, all kinds of creatures on Earth one could regard as intelligent. So chipmunks are always my favorite example because what chipmunks do is chipmunks spend the whole summer, and if you go look outside right now, particularly around Chicago, we have lots of them, they spend the whole summer gathering food. And what they do is they put that food away in their burrows to be there as a food supply for next winter. That's planning ahead, right? And that's an evidence of intelligence. Okay, and so intelligence on Earth is extraordinarily widespread. Okay, particularly if you look at just behaviors that you and I would regard as intelligent. Okay, now the problem with it is that on Earth, all intelligence is roughly the same design. Everything on Earth has kind of central nervous systems with brain stems and neurons that act between ganglia and brain cells and all of that brain activity stuff. And so it's not clear if there is a different or more general form of intelligence that we could appeal to, because all intelligence on Earth kind of seems to follow the same kind of design. So if you're a pessimist, you may think that the development of intelligence once life is around is rare. And if you're an optimist or a principle of mediocrity supporter, then you may think it's more common. And so these numbers here are complete guesses. Okay, so if life is prevalent, you may guess that not very often does intelligent life arrive. Everything stays as plants or algae or something like that. You never get moving, thinking creatures at all. So we're going to take that number pessimistically to be 1 in 1,000. Okay? Principle of mediocrity, we don't know how readily intelligent life exists. One of the interesting facts of life on Earth is, despite the fact that we've been through 5 major extinctions, life has survived through every one of those, and in many of the eras, we see life that has the kind of features that we associate with intelligent life in the modern era. Okay, so for the principle of mediocrity, we're still going to look like we're being pessimistic a little bit, but we're certainly going to be more optimistic than the rare earth folks. Okay, so we'll take the intelligence there to be 1 in 100. Okay. Now, the last number that we care about when we're talking about searching for intelligent life, remember the Drake equation is about looking outward and asking how many intelligent civilizations are in the galaxy that we can talk to, is all about communicative technology. And since we haven't encountered any species yet that has communicative technology like we do, we're just guessing, once again, what the numbers might be until we discover some other planet with life. On Earth, advanced technology is extremely limited. It's limited to humans. We are the only species in all the history of Earth that we know of that has developed radio telescopes, telescopes capable of communicating across cosmic distances with other radio loud civilizations. That is not to say that other species haven't discovered and aren't using technology. As we noted before, there are plenty of species that are using tools like ravens with their sticks. There are plenty of species that have advanced to the point that anthropologists call the Stone Age. So in particular, there are species of the great apes and monkeys, which have entered the Stone Age. So it's clear that technology itself is something that life can readily adapt once it's going down the path of improving its life with intelligence. But it's unclear how often that will lead to technology that can be used to communicate across the stars, okay? So in all the history of Earth, right, there's a 4 billion year history of life on Earth. We have occupied only a small part of it, but there have been plenty of brainiac type creatures before that. We are the only species just now in the last century or so to have radio telescope technology, okay? So it seems like FC probably should be small. So if you're a pessimist, you will say of all the intelligent species, all the intelligent planets where of all the planets where intelligent life has arisen, then only 1 in 1,000 of those does life ever get to the point where it invents radio telescopes. Again, we're going to try and be pessimistic. We don't want to be over-optimistic. But if you think that, sure, someone eventually always will develop a telescope, you'll take a slightly larger number. So maybe 1 out of every 100 worlds with intelligent life eventually makes it to radio telescopes. Okay? Okay, so that's all the numbers in the Drake equation except for L. So if I put them all together in a big table, so I've arranged this from the most pessimistic at the top in the orange, next pessimistic in red, kind of principle of mediocrity baseline there in green, and optimistic there in the bottom. And you can see I've put in all the values. This is very easy to set up in the spreadsheet, and then you can just kind of play with the numbers all you want. You just put the numbers in a spreadsheet, and then you make a formula that just multiplies the numbers together and computes, as I've done over here in the left-hand column, the number of civilizations that have these properties that we will end up being able to communicate with. Now, we don't have the value for L yet, okay? I'm going to do that. So if I just multiply all of these 6 numbers together, you can see what the numbers are over there, but we don't have the value for L. And we're going to have to take an entire half of the lecture to talk about what possibly L might be. The difference between L and the difference between all of the 6 numbers here is that these 6 numbers are all things which are based on the laws of nature and random happenstance in the universe. L is a little bit different because it's a property of the civilization, and it has to do with the sociology and the psychology and the behavior of the civilization, not on the laws of physics, the laws of chemistry, the laws of biology, whatever nature is doing. Okay? Okay, so that's where we're going to end this part of the lecture. Okay, so we have all the pieces of the Drake equation that we need right now, except for that last quantity, L, that you see right there at the end. Next class, next lecture, next half of the lecture, we'll talk about all the different considerations for L, the different things that people have thought about, and we'll dump it all into the Drake equation and come out with a final estimate of what we think the numbers might be. Okay, so that's all I'm going to say right now. Please do take care of yourselves, be safe out there, and I will see you in the next half of the lecture.